So let me look at related rates quickly. Just I think you guys have encountered the chain rule before in an earlier module. So on related rates, there's this problem of a spherical balloon. I trust that you guys would have mastered this kind of problem already. Unless you say it's fine, I can proceed and have a brief discussion on it. Okay. So in the absence of objections, I will just discuss this briefly, go on to the next example, look at something from the exercises, go to the next section, and so on. Okay. So that we're at least on par, everyone. If there's another question that you have elsewhere to ask in the guide, it's also fine with me. Okay. Right. So let's look at this one here. Sometimes it's just a matter of sharpening the basics. So we have a spherical balloon. Well, when they say that to you already, they're hinting at the sphere. Okay. And we know the volume of a sphere is 4/3 pi r cubed. Okay. So spherical balloon is inflated with helium. So I'm just going to write down the data for this problem. I'm just going to write down the data. A spherical balloon is inflated with helium at a rate of 100 pi cubic meters per second, right? So we are given dV dt. How fast is the balloon's radius increasing? At the instant the radius is 5 meters. So now they want the r dt given that the radius is 5 meters. And then they also want to know how fast is the surface area increasing. And we have formulas for surface area, we have formulas for the volume. Okay. You guys can see here, let me just highlight some of the stuff quickly. Yeah, guys, you can see here, you are given that dV dt here in yellow, I mark it, you are given that it's 100 pi. You are required to find the instantaneous rate of change of the radius with respect to time, and also the instantaneous rate of change of the surface area with respect to time. Sorry, given that the radius is 5 meters. You know from your early encounters with surface area and volume that these are the equations for volume, or the formulas for volume and surface area. And what they do is, well, we have dV dt, and then here they employ the chain rule. Here they employ the chain rule, because you can see from here that the volume is a function of the radius. So then they ask, what is dV dr here? And the radius is a function of time. So then they write down the r dt, okay, which they still need to find, though. That's the unknown for us in that problem. Okay. They are given dV dt is 100 pi. And with dV dr, well, this is just differentiation of v with respect to r. You use your power rule there. So it's 3r squared times 4/3 pi. Okay. And you've got 4 pi r squared there. Sorry, just there. That's what you have. Then your unknown here is the r dt, which you need to find there. So, well, what you will do is to get the r dt, you'll just divide on the right and on the left by 4 pi r squared. So you get this. You don't need a calculator for this module, by the way, because that's the exact answer. When you reduce further, when you do your cancellations, you end up with this 25 over r squared. But at the instant when the radius is 5, you do a substitution into r equal to 5 here. Sorry, here in the denominator. Just struggling with this. And a 5 squared, as we know, it's 25. So that's what we have there, equal to 1. So the instantaneous rate of change of the radius with respect to time is equal to 1. Then looking at the STT, the instantaneous rate of change of the surface area with respect to time here. Sorry, that part there. Down here. Using the chain rule, well, we know that S is a function of R, right? So we can get the S dr. We already have the R dt. We just found it, it's 1. Okay. At that instant when the radius is 5, sorry, we find it's 1. Of course, if you just express it purely in terms of the radius, the r dt is 25 over r squared, okay? And if we differentiate the s, or let me say s with respect to r, well, this is just your power rule again. R is your variable here. So you've got 2r times 4 pi, you get 8 pi r. 8 pi r. So from here, I differentiate s with respect to r here. And this is what I get. I put everything together. I end up with 200 pi over r. However, we would like the SDT, the instantaneous rate of change of the surface area with respect to time at the instant r is equal to 5. So when we do the substitution, we end up with 40 pi. Okay. And there are your answers, guys. So the surface area is increasing at the rate of 40 pi meters squared per second when the radius is 5. And as you can see, there's no need for a calculator there. That's the exact answer. Don't go and substitute pi with 3.14. That is just an approximation, a terrible approximation to pi, okay? So leave your answers. You leave it in this kind of form. No calculator needed there. Any questions there, guys? Were you guys clear with that problem when you encountered it the first time, the example?
There is a question, Dr. Sears.
Oh, okay, I didn't see that. Is it okay? No problem. They can ask. No problem.
I have to read this to you.
Okay. Okay. I didn't open the chats now. Okay, sure. Thanks. Maybe I should open the chats.
I think that would be good because for me to have to read to the pi, to the x, to the y,
no,
and
it's
the
fine.
z.
That's fine. Is it Canisile? Canisile?
Yes, that's
okay.
correct.
I have a question on l'Hopital. Okay, good, good. And we have an undefined form, an indeterminate form. She means indeterminate form, but it's not one of the indeterminate forms given in the study guide to use l'Hopital. For example, if you have a limit as x tends to 0 for 1 over x, what reason do we give in brackets for using l'Hopital? You hear me? Can people see the question in the chats there?
Yes, they can.
It's a question relating. Yeah, it's a question relating to l'Hopital, and it deals with indeterminate forms. Okay. So I just wanted to have a sense from Canisile if she have a specific, because it's a bit vague. I have a question on l'Hopital if we have an undefined form, but it's not one of the the indeterminate forms given in the study guide to l'Hopital. For example, we have the limit as x tends to 0 for 1 over x. I mean, there, in that case, your answer is straightforward. It's just infinity. That's all. As x tends to 0, the limit of 1 over x as x tends to 0 is just infinity. It's a standard, it's sort of a standard limit. So you don't need to motivate much there in that case, okay? So this one poses the question that you guys know an equilateral triangle, right? All 3 sides are equal, okay? So they say the area of an equilateral triangle is increasing at a rate of 300 square centimeters per minute at the instant its edges are each square root of 3 centimeters long. So the question is, at what rate are the edges changing at that instant, okay? When they are 3 centimeters long. So there are 2 questions. The area of an equilateral triangle is increasing at the rate. Sorry, it's just one question. The area of an equilateral triangle is increasing at the rate of that, of 300 square centimeters per minute. At the instant, its edges are each square root of 3 centimeters long, okay? So you're given that data in bits, okay? So the question is, at what rate are the edges changing at that instant? So you are given some information, and here's how our equilateral triangle looks like, okay? So you guys will see that you've got 2 sides, length L, and length L over 2 plus L over 2 gives you length L there, okay? And you have a right angle triangle there, 2 right angle triangles there. And from Pythagoras, you are able to find this height here. You are able to find this height using the theorem of Pythagoras. If you say that the square root of L squared minus L over 2 squared, and then you get that height there. This is the height there, square root of 3 over 2L from the theorem of Pythagoras. I don't think you guys have any problems with that, okay? So the area of a triangle is a half base, which you have there. Half the base is L, and then you have a half, and the height you just found out from the theorem of Pythagoras, square root over 2 over square root 3 divided by 2 multiplied by L. And when you do those multiplications in there, in yellow there, this is what you get. I don't think we doubt that, okay? So 2 times 2 in the denominator gives you 4. You get L times L squared. Here the question begs that you must find dl dt, the rate of change of the length of those sides, the instantaneous rate of change of the length of those sides with respect to time. at the moment, at the instant when the length is square root of 3. You are given that the instantaneous rate of change of the area with respect to time is 300. Okay, so normally you start with what you have. But now the area, as you can see here, is a function of length. The area is a function of the length here. Okay, so we start with the ADT, which we already have. We are given 300. And then we use the chain rule. We start outside with the ADL, and then we go inside with the LDT, which we need to find, okay? This is the unknown, the LDT. So we have the ADL, we can differentiate that. And from here, if you look at the ADL from here, well, it's easy. The ADL from here, let me just try my best handwriting here, guys. Well, it's equal to, just going to write down here. So here, use the power rule here. Square root of 3 over 4 is a constant. So we've got 2 over 4 times square root of 3 times L. Okay, so that you're left with this part here. And then you divide 2 into 4. So you're left with square root of 3 over 2 times L. You do not know what is the LDT at the instant the length is square root of 3. However, you know the ADT, it's 300, right? You know that. So now you can make the LDT the subject of this equation here. Make it the subject of this equation here. You've got the ADT. The ADT is 300. And then you invert this here. So you have 2 over, because you are dividing now. You're dividing the left and the right-hand side by square root of 3 over 2 times L, so that you have the reciprocal of that. And you do your substitution at the point in time when L is equal to square root of 3, yeah. And square root of 3 times square root of 3 is 3, so you have 2 over 3 multiplied by 300 gives you 200. Okay, great. Any questions there, guys? Is that how you understood that problem also? Okay. Right. Then the problems of the cone. Once you understand, I think the 2 first basic problems, the rest go relatively the same. It's just a question of using some ingenuity here and then using some, for example, this kind of problem on conical tank in the shape of a cone, conical shape of a cone. There you need to remember the fact that the volume is 1 over 3 pi r squared times the height. And here we denoted the height as x, and sorry, the height is y, and the radius is x in this case here that I marked yellow. And then they just use the fact from similar triangles from geometry in high school, where BC over AB is BD over AE. You guys would have encountered it. So here and there you have to use some memory and ingenuity to resolve the problems. I hope whatever doubts you had on that section, you're fine with it, with these 2 examples. If there's any other question that you had on that, it's fine, I can look at it for you. Okay, so let me pause there. Any other questions, guys, before I proceed to graphs and functions? Any questions on L'Hopital, specific questions on transcendental functions?
I put a question in the chat.
Okay, let me check.
Yeah.
Thanks for that. Let me check. Sorry for that. Where's the chat? Okay. Is it okay? Is it Canisile?
Yes.
Yes, it's that. Would it be possible
to do a question from assignment 1, which is already past due? Oh, okay. Okay, that's fine. Let me just write this down. The limit. Let me just try and write this down if I can move it out. Actually, just help me there. Can you see? Let me just make sure that I write on the correct thing there.
Okay.
You say it's the limit as x tends to, okay, it's cos 2x to the 1 over x squared.
Yes.
Right. And I would assume it's that whole cos, is it? Yeah, the whole, yeah, cos 2x all to the 1 over x squared. And it's the limit. Where's this thing now? Did I miss something now? And it's the limit as x tends to 0, right? Yes. You said you arrived at the limit, blah, blah. Okay, we'll look at your answer again. Let's just see, as x tends to 0, right? X tends to 0. Okay, so can you see that's of the form 1 to the infinity? Let me just open the whiteboard. So let me just write down the problem and then share the whiteboard with you guys. Okay, cool. So this is the problem that I'm writing down, and can you see that? Will correct me if I'm wrong. It's the limit as x tends to 0 of cosine of 2x to the exponent of x squared. Is that the exact question, Kanisila? Is that the exact question?
That is the question, yes.
Right. So if you look at it, let me write in brackets in the interim. So you know that if I substitute x directly in cos of 2x in the brackets here, if I substitute it, I get cos of 0, which is 1, right?
Yes.
Okay. Cosine of 0 is 1. And you know for this exponent here, as x tends to 0, this thing tends to infinity. So it's of that form 1 to the infinity. Can you see that? Right?
Okay. Yes. Yeah.
Right. So normally, what the guys do with such problems, with such problematic exponents, they, because of the continuity of the ln function, they would introduce the ln here, the ln function here. Okay. They would say, because it's a continuous function, so they introduce the ln function so that you have the limit of, so the ln of the limit is x tends to of cosine 2x, and that argument is raised to the 1 over x squared. Okay, and then we use the laws of logs, but we first interchange the limit with the ln. It's quite legitimate. It's quite legitimate. This is equal to the limit of the ln, limit, because by virtue of the continuity of the natural log. Okay, the limit of the ln of cosine 2x, and that cosine 2x is raised to the 1 over x squared. Right? You would encounter that kind of. Let me just save some space and do this. Okay, now let me use the third law of logs. Third law of logs, because the natural log is just a special log, but it's a log. Okay. Then I do this. I'm using the third law of logs now. The limit ln of cos 2x. Do you guys recognize? The third law of logs there? That I shifted the exponent in front of the ln. Look here, guys. Okay?
Yes, I do.
Good. So now you can see that this is of the form 0 over 0. Well, let me just be careful there. Well, I can't say that. Yeah, well, look at if I make x 0 here, cos of 0 is 1, right? What is the ln of 1?
Oh, it's 0, yes.
0. And then in the denominator, I've got x squared. Can you see that? It's 0 over 0. So now I can start doing my differentiation. Okay. And this equates to the limit as x tends to 0. Now I differentiate. The derivative of cosine is minus sign, right? And the derivative of 2x is 2. So it's minus 2 sine 2x, right? And the derivative of x squared in the denominator is 2x, right? So I've got this kind of thing. Can you see that? Can you see that?
Yes.
Good. So what do I have now? I have again a form. I have another form again of 0 over 0. Can you see that? Sine of 0 is 0. 0. So 0. So I differentiate again. So I've eliminated that. Remember, this is minus. I can put a minus outside. I can just put it outside there. Limit, sorry for my handwriting, is x tends to 0. Now let's differentiate sine 2x. It's 2 cos 2x, because this is again, like I said, this is again 0 over. So I'm differentiating sine 2x. I've got 2 cosine 2x. What is the derivative of x? 1. Right? Now I substitute 0 there. I've got cosine of 0. The answer is equal to 2. Okay? -2. I forgot the minus sign here, guys. Remember this minus sign? But that's not done yet. What do I need to do now? I still need to do something.
I think you're gonna say it's gonna be e to the negative 2.
Good. By virtue of this fact. So let me just write a little fact here for you. Why that is so? Because you are correct now. The answer is actually e to the -2. If I say to you e to the ln x or e to the ln f of x, right? This is just equal to f of x, okay? So now what I do is I raise everything on the left to the e and everything on the right to the e. So therefore, my final limit, therefore the final limit of the original problem, the limit of, what was it, cos 2x to the 1 over x squared as x tends to 0. Now, as you said correctly, it's e to the -2 by virtue of this fact here. And there is it done. Okay? Does that solve that?
Yeah.
Okay, great. You understood that, no? I trust the other people also understood that, guys, okay? I remember when you have got these awkward forms where you have an exponent and you have the base and you have these forms 1 to the infinity, most of the times you resort to employing the natural log to help you there, okay? And use those rules. And then ultimately, like Kanisira said, you raise this -2, you raise it as an exponent e to the -2. So that's the power e to the -2. And you leave your answer in that form, or you just write 1 over e squared, okay? 1 over e squared if you want to, okay? Right. Okay, that's a nice question. Let me check. Are there any other compelling questions, guys, that you have there? Any other compelling questions? I like that question. Okay. If there are no other questions, guys, we'll then just proceed with graphs and functions. Okay. Guys, can you hear me?
We can hear you.
Okay, great. So you don't have any other compelling questions there?
Nah, like it's on solids of revolution and we are on graphs, so
Is it busy with the graphs now, no? Okay,
yeah.
so let me go through it quickly, and then because it's some of the stuff that you would have encountered at some earlier stages of your careers, mathematical careers, you would have encountered some of those things. Okay, so let me just share the guide with you guys. Share the study guide with you. Let's get graphs and functions. Okay, so here we look at the notion of sign patterns, and so here we check over which intervals the given function f is negative and over which intervals f is positive. The intervals where the graph of a function f rises and falls, we can use the first derivative there. And also with regard to concavity upward or downward, you use the second derivative there. Okay. I think you guys have encountered that kind of thing. And of course, you must make sure that whatever you do with a function, or its derivative and first derivative, you must make sure it's fully factorized, okay? And then you consider each of these factors with a sort of a test number that lies in a specific domain, and you check what is the sign of that factor and so forth. Right. Let's look at the first instance where we have intervals where f is positive and intervals where f is negative. Okay. So we were given a function and then we probably factorized it into its factors in the numerator. Those three factors there, say. We got that. And then we had the factors in the denominator, say there, x and x plus 4. Okay. Right. So you guys can see that this function is not defined. This function is not defined when x is 0 in the denominator because we can't divide by 0. So that's why we say it's undefined at 0 there, okay? Undefined. You can also see that it's not defined when x equates to -4, because we can't divide by 0 in the denominator again. As you can see, look at those factors x and x plus 4 there. So it's undefined at 0 and -4. And then, and if you look at 2, and we look at -3, and now my focus would be on the numerator. If you look at 2, we will have 0. The function will be 0. If at -3, the function will also be 0. And if you look at 5, the function will also be equal to 0, looking at the numerator, okay? So now it's up to us now to decide how we're going to look at these intervals and look at a test number within a certain subset, okay? So the function we see, as I said, it's undefined at -4 and 0, because you can't divide by 0. And the kind of intervals or the intervals that we'll be looking at, well, obviously it's the open interval -infinity -4, because it goes on here to the left here, right? And we will also look at the interval, the open interval, so between -4 and -3, what's happening here? We'll look at that in between there, right? We'll also look at what happens between -3 and 0, that open interval, and between 0 and 2, and between 2 and 5, and again, the open interval 5 to infinity, okay? This one here, which is represented somewhere here. Just struggle to draw this now. Okay, anyway, somewhere there, there's my cross. The cross showing goes towards infinity. So before we look at that answer, guys, can I ask you a question? Let's look at the interval. Let's look at what will happen with a factor x -2. Let's look at x -2 in the numerator there. And let's see what happens with that factor when the x value lies between -infinity and -4. Can anyone tell me whether this will be positive, or x -4 will be positive or negative? Let's see quickly. Let's just see. We're looking at it over the interval -infinity -4. Let's use -5 as a sample point lying there in the interval. If we substitute -5 into the place of x, what do we get? We get -7. Can you see that? So that x -2 is negative in that open interval -infinity -4. As you guys can see also here, here's that negative. In that interval -infinity -4, that open interval, x -2 is negative, okay? If you look at x -3 now, they say also it's negative, because if you take a point there less than -4, like -5, -5 plus 3 is -2, okay? And if you look at -5 over that interval -4 -infinity, let me just undo this part here. Just undo this part here. So if you look at x -5 and you use, let's say, a number -6 in that interval -infinity -4, you will see that that is also negative. -6 -5 is negative. And the same applies to x, and the same applies to x plus 4. And so you go through all those intervals there. Interval -infinity -4, you saw the signs of the factors. And of course, once you take the function together, it's the product of x -2, x plus 3, x -5, divided by x times x plus 4. These are all negatives, negative, 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 negative. Okay, so what we've encountered, and I hope you guys are with me, for the open interval -infinity -4, okay, and there I've got that wrong thing again. For that open interval, we saw that the factor x -2, we saw that the factor x -2 is negative, x plus 3 is negative, and so forth. So when you look at the product of the numerator with the negatives there, well, it's a negative and it's a negative gives me a negative, and I divide it by the two negatives in the denominator, which is a positive, I ultimately get a negative. Okay, right. So I've got in the numerator a negative factor, the product of negative factors, okay, which gives me a negative in that case. Divide by the product in the denominator of two negatives, positive. So we go through the same range. If you now look at the interval, say -4 to -3, that open interval. Now you take a point there that lies there. Well, if you take any point between -4 and -3, you can take the point, say -3.5 something. If you put -3.5, and there again. Sorry for that, guys. It was me again. And then you go through the whole range again like that. If you put, say, the sample point -3.5 in there, you say -3.5 plus 4, you get a positive. And again, in the numerator, you have the product of three negative functions. Negative times a negative times a negative times a negative is a negative. In the denominator now, well, x is negative and x plus 4 is positive. So you have a negative, right? You have a negative in the denominator, and that division gives you then in total you have positive when you do the multiplications and divisions. Okay, so it means the function is positive in the interval, open interval -4, -3. And in a similar way, when you do it for these factors over the interval -3, 0, you'll find the function is negative. And the same for the interval 0 to 2, the open interval, you'll see that that function is positive, right? Get the thickness sorted, guys. Right. Right. And again, for the open interval 2 to 5, you can use a sample point 3 there. And if you substitute 3 minus 2, it's a positive. 3 plus 3 is a positive, and so forth. And then you can also look at the open interval. You can also look at the open interval there, 5 up to infinity. You can use the number 6, for example, because 6 is greater than 5. You say 6 minus 2, you get a positive. 6 plus 3 is a positive. 6 minus 5 is a positive, and so forth. Okay, right. Any questions at this stage? Is that how you guys also understood that? Huh?
Question.
Yeah. Okay.
Sir, can you like go above a little? Yeah. So
okay.
on y is equal to z minus 2. That on the z, that's where you substitute the number on your timeline or graph. Okay.
Lerato, can you just repeat that question again? Sorry.
Like on the left side, there is y equals z minus 2, y equals z plus 3.
X minus 2, x plus 3, sorry. X.
Yeah. Oh,
X.
it's x. Oh,
X,
sorry.
yeah, sorry, I was wondering where's the z coming from. Yeah, okay.
Okay. So you substitute on the x, not on the y.
You substitute on the x, yeah. That y is just arbitrarily given. I could have called it y1 equal to x minus 2, y2 equal to x plus 3, y3 equal to x minus 5. It's just to denote those factors. That's all, you know. So a better notation would have been y1 equal to x minus 2, y2 equal to x plus 3. But your substitution will occur with the x variable. Okay. So you choose any number lying between -4 and -infinity. Okay. And then you substitute and you check the sign every time. And then ultimately, when you put everything together, you check the sign of f of x, doing your multiplications in the numerator and your division in the denominator by the denominator. Okay. Then you check your overall sign of f of x. That's all you do all the time. You check it for each interval. You take a typical element in that particular interval. For example, the interval -4, -3, that open interval, I can use maybe -3.5. Nicely there between -4 and -3, right? I can use that. And now I substitute, say, I substitute -3.5 in the place of x. Yeah. And I say -3.5 minus 2. Well, it's a minus, right? -3.5 plus 3, it's a minus, and so forth and so forth. Okay. Are you okay with that, Lerato?
I'm fine with the substitution.
Like
So
every time you substitute, yeah. Okay.
Normal, these questions always comes with like points where the graph rises and what.
Yeah.
So
Yeah.
the negatives, it's where it decreases, and the positive.
Careful now. Now you're making reference to the first derivative there, or perhaps the second derivative. Remember, when f prime of x is positive, which means there's an increase in the function. When f prime of x is negative, there's a decrease in the function. Function is decreasing, right? So just be careful when you say decrease and increase, positive or negative. On the other end, when the second derivative is positive, the function is concave upward. If the second derivative is negative, the function is concave downward. So just make sure when you reserve your terminology for the appropriate function type or derivative or second derivative, okay? So here, the negatives here of f of x just shows you that, well, if f of x is negative, it means less than 0. If it's positive, it's greater than 0. Negative, less than 0, and so forth, over those particular intervals, okay? So this means, for example, for our case here, f of x negative between minus infinity and minus 4 means it lies below the x-axis there. It's negative there. There's negative values, right? For the interval minus 4 to minus 3, it's positive now. It's above the x-axis. Can you see that? For the interval minus 3, 0, that, oh, sorry?
I said I can see.
Okay, great, yeah. I just didn't want you to mix it up with first derivatives yet, okay? Yeah, because you spoke of increasing and decreasing functions, right? Right. Okay, cool. So then they have another function there, and here they just note that they note the following here, that for this particular function, not all the factors that occur here will change the sign. For example, this factor here, this sign will always be positive of this one here. I marked. This one can be 0 or positive, but it's always non-negative here. So the main two factors to look out for is x minus 2 and x minus 3. Because those ones can change sign, okay? Yeah. So the ones that really do not pose a problem is this here. So this will always be positive, right? And this will always be, this one here that I already marked in the denominator is always non-negative. It can be 0, but it's non-negative. So the ones of interest really are x minus 2 and x minus 3, sorry. X minus 2 and x minus 3 there. They're the ones that you should look out for, right? Okay. And then, of course, people, they always check where you can get the zeros, where is this undefined. We know, for example, at x equal to 3, this is undefined, this function is undefined, x equal to 3, undefined, because we can't divide by 0 in the denominator here. Can't divide by 0. And also when x is minus 1, it's undefined, because we can't divide by 0 in the denominator, okay? And also, but for x equal to 2, we know it's 0, and so forth, okay? Right. So they're just showing you that there. And here's the point I wanted to stress with intervals where the graph of f rises and falls now. This kind of scenario. This deals with the first derivative, okay? There we just looked at the function as it is, as it was. We just looked at it and checked and factorized as fast as possible, and then check the signs of the different factors within the different open intervals, right? Provided we get a test value from those intervals. So the derivative test to find intervals where the function f is increasing and decreasing is as follows. So if you suppose that f to be continuous on the closed interval ab and differentiable on the open interval ab, if the first derivative is positive for all x in the open interval, it means that f is increasing. On the other hand, if the first derivative is negative for all x in the open interval ab, it means that f is decreasing on the closed interval, right? And here is a first derivative of a particular function that they found. So here's the function f. You guys can get that derivative, right, guys, using the quotient rule, right? You can move from here. You can move from here to here easily, right, guys? Using the quotient rule, because here you have a function f of x equal to, let's say, g of x divided by h of x. So here they're looking strictly at the derivative of this thing now. Of course, bearing in mind the function is increasing where f prime of x is positive and decreasing where it's negative on a particular interval. So here they use the quotient rule to get the first derivative, and this is what they ended up with. Remember with the quotient rule, guys, you first differentiate the top function, right, with respect to x, where there you have 2x, multiplied by x plus 5 minus x squared minus 16 times the derivative of x plus 5, which is 1, right, divided by the square of the denominator function, okay? And then there they simplified as far as possible. That's what they get there. I trust that you guys won't have problems with such a basic derivative, okay? So now they look at the factors of the first derivative. They look at the factors of the first derivative, yeah. Look at x plus 8 in the numerator, x plus 2. And in the denominator, they look at x plus 5, okay? Which is always, anyway, non-negative, okay? Right. So now they look at the intervals, the main points here. Well, this function is 0. F prime of x is 0 when x is minus 2, right? And it's 0 when x is equal to minus 8, as we can see there. Of course, at x equal to 5 in the denominator, it's undefined, okay? Undefined there. So, which means that our intervals are already defined in a way, it's already set. So we look at the interval minus 8, minus infinity, minus 2 up to infinity there. Just delete that part. And we look at the interval, also this interval between minus 8 and minus 5, the interval between minus 2 and minus 5, okay? Look at that. So there are 4 intervals of interest there, okay? Right. Again, you use a test or you use a sample of a point that lies between, let's say, between minus 8 and minus infinity. I can use minus 9, for example. If I say minus 9 for this function here, minus 9 plus 2, it's a negative. Minus 9 plus 8 is a negative, right? And then I look at the function. This denominator is always non-negative. Okay, it's always non-negative. So a negative times a negative gives me a positive. And the denominator is always non-negative, x plus 5 squared, okay? Right. And if you look at the interval minus 8 to minus 5, well, we take a number there. Let's take minus 7. Let's take minus 7. Minus 7 plus 2 gives me a negative, right? And minus 7 plus 8 gives me a positive. And then a negative times a positive gives me a negative. Of course, the denominator is always non-negative. And you go in that fashion, you go about in that fashion. So you can see the cumulative effect of that is that the first derivative is positive for the interval minus infinity minus 8. So it's increasing over that interval. However, it's negative for the interval minus 8 minus 5. So which means it's falling there, it's decreasing. And again, decreasing right through for minus 5 minus 2. And then it rises again for the interval minus 2 up to infinity. Okay, so that's what the first derivative test shows you there. Are you guys clear on that, guys? With regards to concavity, this is something that I've stated previously, guys. If you now explore the second derivative, so intervals where the graph of f is concave up. Concave up, guys, means the following. Do something like this. Just try and draw it. It means concave up. Concave down is something like that, okay? For concave down, this case here, where you have a maximum, the second derivative is negative. The second derivative is negative for this case that I've ticked here. For this case, for concave up, this case here, the second derivative is positive, okay? So if you suppose that the second derivative exists in an interval I, if the second derivative is positive on I, then the graph of f is concave up, like this case, the first drawing here, I've done here. And if the second derivative is negative on I, it's concave down on I. Okay? And there they just check it again. They get the function f. They get f prime for this function here. They get the first derivative, which we already found. They multiply out the numerator function so they can establish easily the second derivative. Of course, 18 is a positive function, right? It's a constant. It's positive. So they just consider the undefined point. So the intervals here would be minus infinity minus 5 and minus 5 infinity. And then they just check a particular value there less than minus 5, like minus 6 plus 5 here will give you a negative. And then, of course, 18 is positive, so the second derivative will be negative. And again, for the interval minus 5 up to infinity, we can take any value there. Let's say minus 4. Minus 4 plus 5 gives you a positive. So the second derivative is positive. Like I said, x plus 5 is non-negative anyways, okay? So, but of course, if I look at it over different intervals, I can see that x plus 5 is negative for the open interval minus infinity minus 5. However, for the interval minus 5 up to infinity, x plus 5 is positive, and the second derivative is positive there. So which means that the function for the open interval minus infinity minus 5 is concave up, so it's concave down. And for the interval minus 5 up to infinity, it's concave down, okay? Concave up, sorry, concave up. In this part here, it's concave up. Okay. Right, guys. Any questions there, guys? Have you guys looked at the exercises also? So if you look at concavity, concave up, concave down, look at the second derivative. If you look at where the function is rising or falling, look at the first derivative sign. Otherwise, if you just have the function as it is, do the factors the normal way and get the function value after multiplying and dividing by the factors, the signs of the factors, okay? Right. Okay, guys, were there any problems when you looked at the examples, when you looked at the exercises that they gave you? Were there any problems that you guys encountered? Or was there any other question pertaining to L'Hopital's rule or transcendental functions maybe that I can look at also? Can you guys hear me?
Yes, we can hear you.
Okay, Lerato. So my question is, were there any other problems that you guys had other than this?
No, like say,
yeah.
Have you seen a cubic function, how it is?
Yeah.
So does it have? Can it have?
Looking at this kind of function, let me just see if I remember correctly. That kind of function, right?
No, the one that has 3 bumps.
One of these 3 bumps. Is there any particular? This is the standard one, y equal to x cubed, right?
Yes.
No. I should draw it like this. Actually, sorry. Just a correction there. I should draw it like this. Sorry, that's not good. That's bad. Let me just erase this. I should draw it like this. Let me just. It's not supposed to be flat like that. But this is your standard cube. Is a Cartesian plane. It goes something like this. Actually, sorry. Okay, that's more like it. Yes, sorry, that was too flat when I drew it there. Okay, so was there any particular cubic function that you wanted us to look at?
No, I just wanted to ask about this one here.
Oh, the one that I've drawn now, the Cartesian plane, yeah. This ugly drawing of mine, yeah.
Can it have?
Okay. You're saying, Lerato?
Can it have like a point of inflection? This one.
Yes. There's a point of inflection exactly here at 0, 0. And x is 0 and y is 0. Why do I say that? Remember, for point of inflection, I look at the second derivative and I put it equal to 0. So if you look at the second derivative of y equal to x cubed, let's get the second derivative of this one. Well, the first derivative
is equals x squared.
First derivative is 3x squared, right? First derivative is right, and the second derivative y double prime is equal to 6x. And if you put this equal to 0, you put the second derivative equal to 0 at the point of inflection, well, for if 6x equal to 0, it implies that x is equal to 0, right? And if you substitute x equal to 0 back to the original function, then y is equal to 0. So this point here, when x is 0, y is 0, the origin is the point of inflection. Remember, it's a point where the function changes direction, okay? Changes direction. Okay. So it's where the second derivative equal to 0. Okay.
Yeah, no problem.
Great. And you can also see that over the interval 0 up to infinity, if you get the first derivative there, let me just write it down again. So I want you to look at this interval here. I want you to look at this interval 0 up to infinity, okay? I just want to say something about rising and falling functions. If you look at the same function y equal to x cubed, same function, the same cubic polynomial, if you get the first derivative, you get 3x squared. Look there, this value is greater or equal to 0, which means it's rising here. It's rising for this interval 0 up to infinity. It's positive, greater or equal to 0, okay? However, yeah, it's fine. So it's rising there, and you'll see that, it's always positive, this first derivative, even for values for this interval here. Even for this interval, it should be open here, guys, not closed, should be open here. Even for this interval minus infinity, and let's say 0 here, right? You will see that y prime is still positive. Right? It's 0 here, but the first derivative function, the slope of the tangent line cutting any point there is a positive slope. The slope of a tangent line cutting any point there is a positive slope, which means this is a rising function through the whole of the real numbers from minus infinity up to infinity, okay? Right. So it rises, it never falls, okay? The first derivative is always positive or 0. Are you clear with that, Lerato?
Yes, we are clear.
Great. Okay, so if there's nothing else, guys, and you're fine with that section, then we can move on. I'm not sure if you guys have looked at some of these work problems here. You can see the screen, right? If you've looked at the work problems, or you want us maybe to move on to some new work, because my understanding is that you guys have already done assignment 1, or it's late or something, I'm not sure. Let's look at a particular function, guys. Let's look at a function quickly. Let's try and sketch this the graph of this function, okay? Let's try and sketch the graph of this function, yeah. Let's just have a quick discussion on it. It's worked out for us. So what they say, you have to determine the x and y intercepts of the graph, as you can see under the A part there. You must determine the vertical and horizontal asymptotes of the graph of f. And you must use the first derivative of f, the sign pattern of f of x that we've encountered, to determine intervals over which the graph of f rises and the intervals over which it falls. And also find the local extreme values, local maxima and minima inflection points. And then use the second derivative of f, or the sign pattern of f double prime, to determine the intervals over which the graph is concave up. That is when f double prime is positive, and intervals of which is concave down. That is when f double prime is negative. And again, use the sign pattern of f double prime and determine the inflection points. Remember, for inflection points, the second derivative must be put equal to 0. And then you can get the gradient of the inflection points. And then by virtue of all the data that you have above, you can now draw the graph of f, okay? If you guys are okay, we can look briefly at this in a very succinct way. We can look at this function here, the graph of this function, try and draw the graph of this function. So what I'll do is I'll just go through it. and just make some notes on it as I go along. Just make this a bit so thick. Right. So let's attempt to draw the graph of this function f of x equal to 4x divided by x squared plus 4, okay? Let's get the x and y intercepts here, guys, right? If we put x equal to 0, you will see that if you put x equal to 0, then f of 0 is equal to 0. Because in the numerator, you've got 0 divided by 0 plus 4, which is 0, right? So that our x and y intercept is 0, 0. Okay, so this is our x and y intercept. The graph of this function goes through the origin there, clearly. Now for the asymptotes, we let x tend to infinity. We check the limit as x tends to infinity of this, right? And there we divide by the highest power in the denominator. The highest power in the denominator is x squared. So we divide the numerator and the denominator by x squared, and this is what we end up with. And in the limit as x tends to infinity for the numerator, well, I get 0. So if there are no questions, I'll proceed, guys. So clearly the x and y intercepts, we've got them. It's the origin. And the graph goes through the origin. And now we're checking the horizontal asymptotes. Okay. We let x tend to infinity, and we see that y tends to 0. So that y equal to 0 is called our horizontal asymptote. Okay. We know where y0 is. Okay. And in the next instance, we get the first derivative of this function f of x. There, from here, we're trying to get the first derivative. Well, we just take out the 4. We just factorize. We just split up 4x. We keep the 4 outside because it's just a constant, and we differentiate. We differentiate this function here. I'm trying to circle here. We differentiate this function here. Okay. Using the quotient rule. And then ultimately, combining that, this is what we end up with after factorizations also, guys. Because now we're aiming at using the sign patterns again for the first derivative, okay? Because this will tell us where the function rises and falls over which intervals. Clearly, if you look at the numerator of this function here, this function f prime of x, the first derivative is 0 when x is 2 and minus 2, okay? And of course, the denominator stays non-negative, so it has no bearing on the sign of f prime, okay? So if you look at the interval, because we said the main points to consider here are the points 2 and minus 2. So if you look at the interval minus 2 up to minus infinity, this interval here, so this part here, if you choose any value less than minus 2, say minus 3, and you substitute in the place of x every time, you get your corresponding values of your factors. And after multiplication of a positive with a negative, you get a negative. Remember, the denominator has no bearing on the sign, it's non-negative, okay? Right. Then if you look at the interval, minus 2 to 2, that open interval, and you take any value there, let's take the value 0, it lies in that interval. 2 minus 0, well, it's a positive. 2 plus 0, well, that's a positive. And then the whole function f prime of x is positive. And in the same manner, we look at the interval 2 to infinity. Sorry, guys, 2 to infinity. Look at that interval 2 to infinity. And we take a value that, let's say 3. Then 2 minus 3 is minus. I substitute in place of x3. And 2 plus 3, well, that is positive. And a negative times a positive is a negative. So that over the interval minus infinity minus 2, the function falls. And over the interval minus 2 to 2, the function rises, it's positive. And for the interval 2 to infinity, it's negative, so it falls again. So we know that. Okay. Any questions at this stage, guys? Are you guys fine with that? Does it make sense? Okay. Right. And then for local minimum, remember, the first derivative, if I want to establish where local maximum or local minimum is, I get the first derivative, I put it equal to 0. But we already established that there are 2 points, x equal to -2 here. Let me just do this quickly, erase this part quickly, guys. We already established that that derivative is 0 at x equal to -2 and x equal to 2. We already looked at that, right? And then we find the corresponding y values at -2 and 2, going back to the original function. We go back to the original function, and I substitute in here. I substitute in the place of x equal to 2. I say, well, what is f of 2? What is f of 2? Well, I've got 8. I've got 8 in the numerator, and then 2 squared is 4 plus 4 is 8 is equal to 1. So that when x is 2, f of 2 is 1. Yeah. And we look at the other point that makes that function to be 0, f prime of x to be 0. Well, that point is -2, as we said, and we calculate f of -2 in the original function. When we substitute f of -2 in here, we get the function value, it's -1, right? So we have a local minimum at -2, -1, and a local maximum at 2, 1, okay? Right. And then for concavity up or downward, we get the second derivative. So we work with the first derivative. We work with the first derivative, and now we get the second derivative. And in fact, we use this first derivative here in this form that we gave it. Let me just note that, guys, because it's easier to work with it. So if you look at the first derivative here, where we calculated it here, it's easier to work with it. And this will help us to decide on the nature of the concavity, okay? So that ultimately, they reduce this whole thing, second derivative, to this. And you guys can see that in the denominator, well, there's a cubic cubic function there. Well, to the degree 6, actually. So it's greater than cubic. You can see that this function here will always be non-negative here, okay? In fact, it will always be positive in the denominator of f double prime. So the main functions to consider are those factors in the numerator. You have to consider 8x minus 8x. You have to consider the square root of 12 minus x and the square root of 12 plus x. Those are the main ones to consider. Of course, if x is square root of 12, well, the second derivative is 0. So there's an inflection point there. By the same token, if x is equal to minus the square root of 12, the second derivative is 0. So we have an inflection point at minus the square root of 12. So the function changes direction there, okay? That's one thing we know. And then ultimately, when we look at the interval minus infinity up to minus square root of 12, we use our test values there, and we check the values of each of these factors, pretty much like we did for f, the original function. So that ultimately we see that f double prime of x, well, it's negative for the interval minus infinity up to minus 12. It's negative there, right? So which means we have there'll be a maximum occurring there. So it's concave down. For the interval minus 12 to 0, it's concave up. And for the interval 0 to 12, it's concave down. And again, concave up for the interval square root of 12 up to infinity. Okay, right. And like I said, guys, for inflection points, I mentioned that x is equal to square root of 12. So I have to find the function, original function value at square root of 12. And again, the other inflection point that makes f double prime to be 0 was minus the square root of 12. You have to determine the function value there, the original function value. So these are the 2 points that they got. They got this here, this point is an inflection point. And they also have that this point here is an inflection point. And there's the graph, guys. So we had a maximum at 2, 1. We had a maximum occurring there. An inflection point, this point here, x square root of 12, y square root of 2 square root of 3 over 2. We had the y and x-intercept 0, 0. We started off with that. We have an inflection point at minus square root of 12 and minus square root of 3 over 2. And we had a minimum value at minus 1, 2. That's where we started. Okay. Right. And we can see that from symmetry, because we have minus x, minus f of x here, and we also have x, f of x. So this graph of this function is symmetric. The symmetry with respect to the origin. Sorry, I was going to say with the line y equal to x. But there's symmetry, it's symmetric with respect to the origin in that case. And there's your graph. Any questions there, guys? I'm going through it in this way because I expect that you guys would have gone through it a long time ago, okay? You guys, I think on in your guide on page 23, there's also a nice little example there. Let's just look at optimization. With optimization, we mean finding maxima and minima, okay? Subject to certain conditions. I think it's page 23. Yeah. There's a nice little example there. Yeah. People, here's a worked example. Can everyone see the study guide with the worked example on page 23?
Yes.
Yes, can you see that? Eh? So what I'm going to do is I'm going to try and write it down, the question on the whiteboard for you, and then we'll look at it. Has anyone had a look at this problem and did they battle with it? Or would you like me to look at another problem perhaps that you sort of battle to understand from the worked examples? Because here they say find the largest possible value of s equal to 2x plus y if x and y are side lengths in a right triangle of which the hypotenuse is square root of 5 units long, okay? So they want the largest possible value of that. And then they have a lengthy solution to this problem. But it works out very nicely though, okay? Works out nicely. So let's look at this optimization problem. I think it falls under optimization problems. It's section 1.3, okay? So let me write down the question for you guys and let's just do a screen share and try and solve this one, okay? Stop sharing. And then I'll try and write it down. Let me share the whiteboard with you. No, let's share the whiteboard with you. Let me write this down, okay? Right. So here they say, find the largest possible value of s equal to 2x plus y if x and y are side lengths in a right angle triangle or in a right triangle which has hypotenuse square root of 5 units long. So we have to find the largest possible value for that function s, function of x and y, okay? Right, so let's do that quickly and let's see if we can find a solution there, okay? So in a right angle triangle, so we've got this kind of scenario. So they say that in that right angle triangle, there's the right angle triangle. X and y are the side lengths, right? X and y are the side lengths. So this length here, the hypotenuse is square root of 5. You can set up an equation already from there. From the theorem of Pythagoras, you can see that x squared plus y squared is equal to square root of 5 squared, which is just equal to 5, okay? And we can write, and we can now express this function in terms of one variable only, because we don't have the tools to work with what we call partial derivatives yet, where we could deal with a function of two or more variables simultaneously. So what we will need to do is express y in terms of x now by virtue of this relationship here, okay? So from here, because ultimately we will want to write this function s in terms of x or y alone, okay? So from here, y is equal to square root of 5 minus x squared, clearly, right? Therefore, s, if I look at my original function s here, I can write y as that now. So that function only becomes a function of x. Remember, I need to find the largest possible value for this if x and y are the side lengths in a right triangle which has hypotenuse square root of 5 units long, okay? Right. So, of course, people, what you'll notice here is that x must lie between, not equal to, x must lie between x must lie between square root of 5 and 0. For this to make sense, x has to lie strictly between 0 and square root of 5. Why is that so, guys? Why is this condition important here?
If x is not between 0 and square root of, there comes an end number. I'm not sure.
If x is equal to, say x, sorry, I didn't hear that part, Alarato. If x is 0, what would happen? If x is 0, but we don't permit a triangle like that with 0 length. Yeah, it doesn't make sense to speak of it, right? To have a triangle with 0 length, okay? It must be positive, so this part makes sense, right? Okay, so there has to be, x has to be greater than 0. X can't be 0 because we don't speak of a triangle of 0 length, with one side of 0 length.